A good logging library is one of the most useful tools in software development, because whether you're debugging a target that's on your bench or deployed somewhere remote, log data can give you invaluable insights into the state of your application. But in resource-constrained systems like microcontrollers, the space needed to store all those log message strings and string formatting code can quickly become a problem. At least that used to be the case. Because for embedded projects written in Rust, there's a popular crate called defmt that makes worrying about log message overhead a thing of the past. So today we're investigating how it works and how to start using it. To set the stage for our discussion about defmt, I've put together a little demonstration. This is a simple program that writes a whole bunch of log messages into an RTT buffer, which is read by the host. Each of these macros is wired up through a feature flag that enables either the RTT target crate, which is our control, or the defmt RTT crate. We've used the RTT target crate in past videos, so the output produced by this code is not surprising. What is a bit surprising is that the space required to store all those strings is not far off from the amount needed for the executable code. We can peek into the read-only data section to verify what's there. And yep, those are the log strings. Now, only the vector table, text, and read-only data sections here actually get flashed onto the controller, so we'll need 16 kilobytes of program memory for this firmware. Alright, 16 kilobytes is our baseline. I think we... Oh... You know what? I forgot about floats. Yep, I've got to add an example of formatting a float. You know, for science. Although, I can't imagine adding this one line is really going to affect the... What? Okay, that's about 38 kilobytes in total. Compared to what we had before, adding string formatting support for floats more than tripled the size of our executable and more than doubled the total space required to store this firmware. If you're not used to building firmware, then 38 kilobytes may not seem like a big deal, but on most microcontrollers, that's pretty easily going to be using double digits of your available program memory. Let's give defmt a shot and see how that compares. Wow. Well, somehow it completely removed all the string data, and the total memory required is now only 6 kilobytes, less than 1/6 of what we had when formatting floats, and less than a half of the original test case. So does this code actually do anything? Huh. Yeah, that looks good. So how does defmt pull off this trick? The log message strings are actually encoded within symbols used in the defmt section. If we look inside that section, we find each value here has a JSON encoded symbol, which includes metadata like the package and crate information, log severity level, and of course the log string itself. But like some of the other metadata sections within the ELF file, this one doesn't live anywhere on the controller. It's just there as a reference for the host application that's receiving the log data from the target. Then what is the target sending to the host? For each log message, the firmware will package up the appropriate defmt section index for the string and parameter type, along with the parameter value itself. Throw in some clever COBS-based encoding for compression and framing, and now you only need to send a handful of bytes instead of a formatted string. This has the added benefit of reducing the amount of space needed in RAM to buffer these outbound messages or send them over the wire. So the D in defmt is deferred formatting. The target is deferring string formatting responsibilities to the host. This of course means that now your log viewing tool will need to have access to that defmt section data for the specific version of firmware that your target is running. On the bench, this isn't a problem because ProbeRS has the ELF file on hand. But if you're remotely collecting logs from a fleet of IoT devices that aren't necessarily all running the same firmware version, then yeah, there's some work to be done on the server side to get those log messages assembled. Which seems like an interesting project. Okay, we've seen how defmt works, so let's go over how to get it set up. Here I've got a very basic no standard project that I want to add logging to. The first thing I'll do is add deformat as a dependency. This crate defines all those logging macros we used earlier. But it doesn't specify where the log data will get stored. For that, we need something that implements the logger trait. This is a job for the global logger, and the one we've been using is deformat RTT, which places the log messages into an RTT ring buffer that gets read by the host. Access is controlled by a critical section, so we'll have to add an implementation for that as well, and make sure the compiler can see them. In order for the deformat section to be included in your generated ELF file, there's a linker script that needs to be run during your build. This is part of the deformat crate, so we just need to update our cargo configuration file to get it to run alongside the main linker script. And while we're in here, we can define the severity level to use for the project by setting the deformat log environment variable. This is a compile time filter, screening out any messages with a lower level, and so this value will have an impact on code size. You can set different log levels for different modules, including those in your dependencies, and these overrides can be chained together in a comma-separated list. An environment variable is also used to configure our global logger's buffer size. And one thing I've found is that you may need to run cargo clean before any changes made here take effect. When it comes to capturing values, deformat does not use the core library's display or debug traits. Instead, it has a format trait that it implements for the standard types, and for the ones you define, there's a handy derived macro you can use. Many no-standard libraries will include an optional deformat feature flag that will implement format on their public types and/or enable logging within the crate. Let's throw an example in here of that as well. Okay, let's see how that looks. Excellent. Now this was a debug build, so there's some handy source file and line number information for each log message that we didn't see in the release builds in part 1. This data lives in the debug sections of the ELF file, and though they are quite large, like the deformat section, they won't go onto your microcontroller, and so there'd be no harm in getting this in our release builds as well. So let's set up a release profile in our cargo.toml that will include debug data and some of the recommended compiler and linker optimizations to keep our firmware as small as possible. So let's test that out. Nice. Great. You can also configure your logs to include timestamps. I'm not going to do that in this example, but if we check the deformat book, you basically just need to provide the timestamp macro with whatever function or method that will return the current time counter value. The last thing I'll say about deformat is that the RTT-based global logger is obviously only useful if you can connect a probe to your device, which usually isn't the case once it's been deployed. The ability to remotely collect log data to debug an issue is something I've personally benefited greatly from in my career, and so we'll look into how this can be done with deformat in future videos. And that brings us to the tail end of this logging story. If you enjoyed this video, please hit the like and subscribe buttons before you go. Thanks so much for watching, and I'll see you next time.